Hey guys, today we're going to be talking about topological sort. And before going into the details of the algorithm, I just want to say that we used to use like the FS to do it, and I thought like using the other way, like the integrated way to do it, like is very interesting, and that's why I'm doing this topic for this week. I really like the method that the professor mentioned in class. Okay, so let's start. So yeah, I look it up online, and obviously it's called like Kant's algorithm. I don't know if that's how you pronounce it. But anyway, so you just compute the integrity for each of the vertex present in the DAG. And by integrity, it means like the number of arrows that point at it. So like, for example, for 2, it has like 1, 2, 2 arrows, like 2 edges pointing at it. So the integrity of 2 would be 2. And for 0 and 4, the integrity of it, this is 1, this is 0. And for 3, it would also be 0 because there is no edges pointing at it. Yeah, so we're going to cap an array where there are nodes and its corresponding integrity inside. Okay, and then we're gonna look through the array and then enqueue the vertices with integrity 0. Like in this case, it would be 0 and 3. And then we're gonna remove a vertex from the queue. But after remove it, we have to decrease the integrity by 1 for all its neighboring nodes. So let's say if we dequeue like 0 from the queue, then we also remove this edge. So for 1, the integrity would change from 1 to 0 because there's nothing like pointing at it anymore. Yeah, so if the integrity of the neighboring nodes is reduced to 0, also the same case, then we can add it to the queue. And for 1, then it will be added to the queue. Yeah, so I think this is a very clear method because you can by doing this, you can guarantee that there are no edges pointing at it before it got dequeued from the queue. So it definitely follows like a strict topological order. And sorry, yeah, here. So this is the same example. I just want to go over it again so I make sure that like I understand and everybody who's watching the video also understands. So here's the array that we kept for 0, 1, 2, 3, 4. We can see this is their corresponding integrity value. And I'm just gonna draw it with like my with my zoom. So here's the queue that we kept. So first we look through the array and we see that 0 and 3 got 0 integrity. So we enqueue it to the queue, and then we output this 0. And we're gonna change this to 0 because this edge is removed. And we're gonna have 0 here, but the new queue would have 3 and 1, right? Because this is changed to 0. And then we're gonna output 3. And for 3, there are 2 edges connected to it. So we're gonna change this to 0 and this to 1. And we're gonna put 4 in it. 2, we cannot put in it. We cannot put it into the queue because the integrity is like still 1. Okay, and then we're gonna output 1 here. We're gonna output 1. And for 1, we can finally remove this edge, and this is changed to 0. So here's 2. And then we're just gonna, like dequeue 4, dequeue 2. So we have 0, 3, 1, 4, 2. Yeah. And there could be other possibilities of doing it. Like this is not only like topological order for this like specific graph, but this is what we got from like using the specific array algorithm that I just mentioned. And the running time would be O V plus E. And this is already like specifically explained in class, so I won't go into details. But yeah, thank you for listening. This is all I have for this week.